Welcome to the afternoon session. We have Moreau, who's going to tell us about Nilpotent orbits in relation to affine algebras.
Okay, thank you very much. I would like to thank the real local organizers and especially Jethro for this nice conference. I'm sorry that I haven't sent the title before. So this is what I'm going to explain today is based on joint work with Tomoyuki and Jethro. And today I'm going to talk about the first part, which is actually a kind of degradation of the second. So the aim of my talk is to relate different notions of associated varieties that are important in representation theory, but that come from different contexts, and then give applications. So the first context is the most classical one, is a context of associated varieties of primitive ideals in the enveloping algebra of a simple Lie algebra. So of UG, and here throughout my talk, G will be a complex simple Lie algebra. So this is now a standard fact that this geometrical tool is a powerful tool in representation theory. And the second context is the context of associated varieties of affine vertex algebras, and more specifically at admissible level. So of affine vertex algebras, so VKG. And here I assume admissible level. So we already encountered this notion in David and Drazen's talk. So let me recall that this means that K plus a dual Coxeter number is a positive rational number, plus some conditions that I will recall later. For the moment, just remind this. And also, as we will see later, the construction is quite different than this construction. It is inspired and motivated by this notion. And here I can tell you right now what are the typical varieties appearing in this context. So in this context, with Q as here, a typical variety that appears typical varieties are the following. So let's denote by NQ, for Q any integer, the following variety consisted of the element of G such that at x power 2q is equal to 0. All right? So this has a priori nothing to do with vertex algebra, but this is what will appear in this context, for example. So it's clear from the definition that this is contained in the nilpotent cone. This is clear. And a deeper result says that this is actually irreducible. So this is not clear from the definition, but it is a fact. So far, there is only a case-by-case proof. But anyway, this is irreducible, and this implies that this is a closure of some nilpotent orbits. For some nilpotent orbit OQ. All right, and the main result I wanted to discuss today is to give a simple description of this in terms of primitive ideal. So this is the main point of the talk. So main result, give a description, a simple description of this closure in terms of primitive ideal. So as I mentioned, this has nothing to do a priori with vertex algebras and also this connection, but I'll prove deeply used the theory of the representation theory of admissible affine vertex algebras, and also I will try to mention motivations and application, in particular to W-algebras. So motivations also come from vertex algebras. So this is the things I want to explain in this talk. And actually, we observe this result in a bigger project on collapsing level, but we find this result interesting in itself. So this is what I want to say today. And after that, more recently, we observe that these varieties, closure, these varieties, also appears in the context of associated varieties related to the small quantum group. So this is the last context. So here, I'm not going to say so much things, but I can explain right now the connection. So the last context is the context of associated variety of the small quantum group. So here, in my notation, theta is a primitive qth root of unity, where q is as before, but here I need to assume that q is odd plus not bad for g, whatever it means. But in particular, it means that, in particular, 3 does not divide q if g has type G2. In particular. All right, and in this case, what is the connection? The statement is the following, is that this closure is actually the scheme, which is reduced, of the cohomology algebra corresponding to this finite dimensional Hopf algebra. So this result actually is not really due to us. We just collect some known results. So let me explain. So this fact is a direct consequence of a result of Ginzburg and Kumar for q greater than the Coxeter number. Indeed, in this case, this closure, or equivalently q, is the nilpotent cone of G. And then they show that in this case, this is concentrated in even degree, and it is exactly the nilpotent cone. So this is direct. And much more recently, there is a nice paper of Bendal, Nakano, Parshall, and Pilen. So you can see here. Is it okay? Okay. So this is from 2014. And in this case, the result is due to us. And this paper was pointed out to us by Anna Laszowska. But then here, the description is slightly different. Actually, what they get is rather... So what they observe is, with this condition, this is actually the closure of some Richardson nilpotent orbit. And in this case, the description can be done as the saturation of some nilpotent radical of some parabolic, which only depends on q. And it is an easy case-by-case verification that their description corresponds to this. So it's not so satisfying so far because we only checked case by case. So there is no conceptual proof of this so far. But this connection suggests a strong connection between representation theory of admissible affine vertex algebras and that of the small quantum group. And this is actually currently studied by Tomoyuki, Thomas Krutschis, and Kazuya Kawasetsu. And this was also mentioned in Davis' talks. There is a connection between these two representation theories. Okay? So I'm not going to say much more about this, but then now I would like to comment this part. And to begin with, I would like to make some recall about standard facts in the classical setting. Any question so far? But I guess here I cannot write, no, because of this. Okay? Oh, it's okay. All right, so here, so G is, as I say, a simple Lie algebra, and then, okay, let's consider a two-sided ideal in the enveloping algebra. So I remind that UG is filtered by the PBW filtration, and the corresponding graded space is naturally a commutative algebra isomorphic to the coordinate ring of the dual. So maybe I should write like this. And so to any such ideal, you can define the associated variety as the zero locus of the corresponding graded ideal. So this is by definition the element in G star such that fx is 0 for all f in grö I. All right, and so you can view it as a variety in G star, but I like to identify with G so that all our varieties will be belongs into G, to G. All right, so now in the case where I is a primitive ideal, so I remind you that this means that I is the annihilator of some simple left UG module. There are two important results, very deep results that I want to recall for the sequel. So I don't state in the chronological order, but the first statement, the first part due to Joseph, and independently by Tanizaki. Sorry for the order, and Kashiwara, says that the corresponding, so I is primitive here. Yeah, so the first part says that this is actually, in this case, contained in the nilpotent cone. So this part is not so difficult, actually, using the result about the center of the enveloping algebra and the description of the nilpotent cone as a spectrum of the it's defined by the augmentation ideal of the G invariant part. But the strong part says that this is irreducible. So as a consequence, this is the closure of some nilpotent orbit. All right, so this is the first result I wanted to recall. And the second, which is due to Duflo, says that if I is primitive, this is actually the annihilator of some irreducible highest weight module. So there exists some lambda in the dual of a carton of G such that I is the annihilator of some, so this is my notation for the irreducible highest weight representation associated with lambda. All right, so there is no, of course, unicity here, but you have a precise description in some sense. But now if you combine the two results, it's natural to wonder what is the connection between this lambda and the nilpotent orbit appearing here as a variety associated to such ideal. So in the case where lambda is integral, so this means that O is what we call a special nilpotent orbit, we have a nice description that I would like to not recall in details, but maybe briefly mention. So maybe just a remark that if lambda is integral, so in fact it's equivalent to, you can take this as a definition, but this is a special nilpotent orbit. And this coincides with the Lustig definition of special nilpotent orbit. All right, so in this case we have the following, the result of Barbash and Vaughan, which give you a precise connection. So I assume that O is special. So yeah, maybe, okay, maybe I want to use a notation for this. It will be G lambda. So this means that this is the associated variety of some G lambda, where the lambda integral. And then in this case, this closure is the associated variety of J with my previous notation of some lambda O that I'm not going to describe, but this is some linear form which only depends on O. You need to use a dual Langlands to define it, but I don't give the precise description. And this is a half sum of positive roots. All right? So, and moreover, this is minimal in some sense. Moreover, this linear form is minimal in some sense. And the sense is the following, that if there is some mu such that this is a closure of similar things, then either mu is this lambda O, or the norm is strictly bigger. So it's kind of canonical in this sense. All right? Okay, so I think it's only it's the only thing I wanted to say in the classical setting, and so now I want to go to the setting of Kac-Moody-Lie algebra and corresponding vertex algebras. Yeah, I think here for this part I need some assumption, but okay. I need that the corresponding dual is even. So in particular, it's okay if O is rigid, but anyway, you need some assumption. But okay. So the second part, so here I consider the Kac-Moody-Lie algebra associated with G, and then corresponding affine vertex algebra. So I'm going to keep Drazen's notation throughout the talk. All right, so here the idea is that to any graded quotient, so that the quotient has a vertex algebra structure, one can associate a certain Poisson varieties, which is what we call the associated varieties, and this construction can be generalized, but in my talk I will explain only this setting. So to any graded quotient of VKG, so in particular we will be interested in the unique simple graded quotient of VKG. One can associate a certain affine Poisson variety that I denote by X VKG. To any graded quotient, let's say V, that I denote XV. So let me explain the definition, the construction in this setting. All right, so I recall you that from the PBW theorem, the VKG as vector space is isomorphic to the enveloping algebra of this, so as vector space. And now I consider a certain quotient. So, okay, maybe here V is as before any graded quotient. And for any such quotient, I consider this quotient of V. And this is what we call the Zoo C2 algebra of V. So, and this is naturally a Poisson algebra, so maybe I just briefly mention the general construction. If V is any vertex algebra, you define RV to be V, you take the quotient by the vector space that is usually denoted by C2V, and where this is the vector space generated by such element. And this is known that this is Poisson. a Poisson algebra. So the product, if I denote by bar the image in the quotient, is given by the normally ordered product. And the Poisson bracket is given by A0B. Okay. And then, yeah, maybe I can say in general, XV is a reduced scheme associated to this Poisson algebra. So in general, if you take the spectrum here, it's not reduced, but in this talk, I consider the reduced scheme, all right? So in this setting, we have an explicit understanding of this construction that I would like to mention. It's a bit more concrete. Okay, so in this setting, we have a map, let's say a map, yeah, from the symmetric algebra to this quotient, sending an element x in G to, so you first take the image in the quotient. I did not here there are too many bars, but you understand. This is the image in the quotient of VKG. And modulo what you divide. Okay, something like that. And in the case where, so let's say this is phi. So if V is a universal affine vertex algebra, then this is an isomorphism. And so you can understand the Poisson structures just by transporting the canonical, the Kirillov-Constant-Souriau-Poisson structure here. And in fact, this construction leads to the same Poisson bracket, of course. So, but in general, if V is just a quotient, then this is a surjective map, surjective Poisson algebra morphism. And then you can understand this variety as a zero locus in G or G star of the kernel of this map. So this is a concrete construction. So in particular, we are interested in, as I mentioned, of the associated variety of the simple quotient. And as you see, the construction is a priori different than the previous one, but motivation are the same. And the idea that this should play the role of associated variety of primitive ideal. So we are interested in this object. And so in general, this is difficult to compute. But for some family of K, we know how to compute this. And maybe I would like first to mention that the main difference is that, in general, this is not contained in the nilpotent cone. So this is the main difference, in general. So to see this, easiest way to see this is that when VKG is already simple, of course, this... Oh, sorry. Yeah. So obviously, if VKG is simple, for example, so if K is generic, then this is simple. And so obviously, this is the whole G. So this is the easiest case. And actually, with Chuipo, Yang, and Tomoyuki, we precise this statement. In the following way, we have the following statement that this is simple if and only if this equality holds. So this gives a geometrical characterization of the simplicity. And in fact, there are also intermediate cases. This means case where this variety is neither G, neither contained in the nilpotent cone. So this will be developed in next talk, so I just mentioned briefly. So remark, there also exist pairs, GK, where X LKG is not contained in the nilpotent cone and also different than whole G. So in fact, for example, a closure of Dix-Mie sheets can appear in this context, and this will be the topic of Chris talk after me. So, for instance, closure of Dix-Mie sheet can appear. So this is of the form, you take the saturation of X for X semi-simple. This is typical example. So this was first observed by Arakawa and myself, and as I mentioned, this was generalized recently by, sorry for the name, Kriska. And okay, so this is first case, and more generally, you can have the closure of some Jordan classes. So which are neither a nilpotent orbit, neither nor a Dix-Mie sheet closure, and this, for instance, Justine Fasquelle have an example in this case. Okay, so there are many other situations, but in this talk, I want to focus on families where the things behave nicely, that is to say, they are similar to primitive ideals, so where we have a nilpotent orbit closure. So in this talk, I want to focus on case where this is a nilpotent orbit closure. Okay, and a nice family, it's admissible level. So for admissible levels, this variety behaves nicely. So I would like to give a more general definition of admissible level. I would like to recall the notion of admissible weight. So this is a notion due to Katz and Wakimoto. Whatever the year. So here I take a linear form on the Katz-Moody-Cartan algebra, and I say that this is admissible if the following two conditions holds. So first of all, lambda is regular and dominant. And second, the vector space generated by the real root lattice must be the same as the one generated by the integral lattice of lambda. So this is... All right, so the condition looks technical, but Katz and Wakimoto conjecture that this condition are equivalent to the fact that the character of the corresponding highest weight module has a modular invariance property. All right? And for the case, so now I remind, so I haven't mentioned, but this is a particular highest weight representation of G hat. And in this case, this one is admissible if and only if, okay, I will say also that K is admissible if and only if, so maybe I write the condition here. No, maybe I write here. So as I already mentioned, this is a sum strictly positive rational number such that so P and Q are coprime, and P is greater than the dual Coxeter number if Q is coprime with the lassity of G and is greater than the Coxeter number if not. So this is the lassity, so this is 1 for type idea and 2 for BCF, 4 and 3 for G2. All right, so now the theorem of Tomoyuki says that if K is admissible, then first of all, the associated variety of LKG is contained in the nilpotent cone, and also it is actually the closure of some nilpotent orbit. But I want to state in this way. So assume that K is admissible. So actually, the statement is the following. So this is the variety NQ that we encountered in the introduction if Q is coprime with the lassity. And this is another variety that I denote L for Langland's dual, and Q if in the other situation. And let me give the definition of the second one I haven't introduced before. So yeah, maybe I recall what is NQ. So NQ is this. But here you can write as highest rate representation associated with the highest positive root. And this one is similarly defined, but you consider the irreducible representation associated with the highest short root. And I have to divide by QR. All right, so it just defined with respect to the highest short roots. Okay? So as I mentioned, this is clear that this is contained in the Nilpotent cone, and this was conjectured by Fegin and Frenkel. But in fact, this is actually irreducible. So these two varieties are actually irreducible, and so this is actually the closure of some nilpotent orbit that I denote uniformly OQ. All right, so this is how OQ is defined in this talk. All right, so in particular, you see that in this case, this is irreducible, and maybe I mentioned some more general conjecture about this, not conjecture, but some general fact about this. So more generally, we conjecture, so with Tomoyuki, that if this is contained in the nilpotent cone, then this is actually irreducible. So I mentioned that there are examples where it is not contained in the nilpotent cone, while VKG is not simple, but there is also example where K is not admissible, and these varieties contained in the nilpotent cone, which are important for other applications. So this is a conjecture, and even more generally. So in fact, this condition is equivalent to say that this variety has only finitely many symplectic leaves, because symplectic leaves are adjoint orbits, and this, okay, it's easy fact to check. This condition is equivalent. As soon as you have a non-nilpotent element, you have infinitely many adjoint orbits in the variety. So more generally, we conjecture that if XV has finitely many symplectic leaves, and plus V simple or whatever you want, it's a conjecture, so we don't really care, then XV is irreducible. All right. Okay, so I think now I can state our main result and say idea of the proof and application. So this is my third part. All right, so as I mentioned, the result will give a description of this in terms of primitive ideals, but since nilpotent orbits appearing in this context are not necessarily special, for instance, in G2, all nilpotent orbits appear in this way, but it is known that at least two nilpotent orbits in G2 are not special. So it's not surprising that the weights that will appear in our result are not integral. If you remember the definition, it should be like this. So the result is the following. So K is admissible, so as usual like this. And then the statement is that if Q is co-prime with velocity, then OQ, so if you want is NQ, is the associated variety of J, so it's rho over Q minus rho. And in the second case, then we just replace rho by rho Ch. So it's quite uniform. All right, so this is a statement. So I would like to first give an idea of the proof. So maybe I like to denote this part, this I will denote by lambda q, whatever the case. And then I introduce the corresponding weight of the Kac-Moody algebra. Okay, so the proof uses representation theory of admissible vertex algebras. Also, as I mentioned, the result has a priori nothing to do with that. So, idea of the proof. So the key point is the following remark. This lambda q hat, so I recall that this is just this. So by construction it has level k, but also one can show that this is admissible with respect to the definition I gave of admissible level. So this is admissible weight, sorry. So this is an admissible weight, and also the integral lattice associated with it is isomorphic to the integral lattice of q lambda 0. So anyway, because of the two conditions, by a result of Arakawa, which was proved previously by Adamovich and Milas for SL2, it implies that L lambda q hat is an LKG module. So this is the key point of the proof. Because of this, now by those correspondence, we can relate the two varieties. There is still some step. So this is the first step of the. So by those correspondence, it implies that the zoos of this, which is the highest weight representation associated with the projection, so that is to say, this highest weight representation is a zoo of this one module. And this is a quotient, a certain quotient of the enveloping algebra. So let's say IK. All right, and so this implies that the annihilator of this one contain IQ. So this is still not connected with the zoo C2 algebra. So now this implies, so this is just clear, that this is contained of the associated variety of IQ. And now this is a general fact that if you consider the graded algebra of the Zoo's algebra, the corresponding spectrum or reduced spectrum is contained in the Zoo C2 algebra. So this is contained in X LKG. So this is a general fact. And actually here, because K is admissible, is equals, but we don't really care for the moment. That spec of Gre Zoo of V, so as reduced scheme, is contained in XV. Okay. And this is precisely our variety or Q bar. And so we have only an inclusion, but the second step is that, in fact, they have the same dimension. So, and because they are both irreducible, this concludes the proof. The second step is less elegant because we use a combinatorial formula, and at some point we do a case-by-case proof. But the second part, I don't detail, but the second part is that using a combinatorial formula of Katz, Elashvili, Katz, and Winberg, we can show that the dimensions are the same. Yeah?
Can I ask you about this equality for K being admissible? What's the statement?
I'm not sure about the statement, but when K is admissible, I think the equality is proved. That's correct? So, okay, I finish here and I put a remark. For any K?
Yeah, so that's the question, is it?
So here you say it's always equal. This I'm sure it's not. So what do you say it's always equal?
Yeah, no, the inclusion is clear, but there was a statement about K being admissible being
Okay, the statement I mentioned after.
Okay.
But, okay, just I want to say that this is the same dimension, and by irreducibility we are done, okay? And this I don't detail. So the remark I made, but I hope it's correct. If K is admissible, here we have an equality.
And it's an equality about variety, so not only.
Yeah, I think it's only about variety. It's not about scheme. This is your question?
Yes,
Yeah, I don't think we know so much about scheme equality. Yeah, by the way, no, I don't have time. Okay. So, so this is about the proof. So as you see, we deeply use this representation theory statement. Also, we conjecture that maybe the equality holds even if we don't have this condition, actually. But the proof doesn't hold. All right, so I would like to say more about this. Moreover, the lambda q that appears in this theorem and in the proof is minimal in some sense, in the sense that it looks like Barbach-Vaughan result. So moreover, so this concludes what I wanted to say about the proof, but moreover, lambda q is minimal in some sense. So here the meaning is this, that this is this highest rate irreducible representation of G hat has a minimal conformal dimension among LKG module in the category OK. So this has a minimal conformal dimension among simple LKG module in the category OK. And in fact, we have similar minimality, slightly weaker results, that in fact, if for any mu, let's say mu hat as before, like this, so admissible plus the technical condition that this is isomorphic to this. So the condition which makes sure that this is a LKG module, such that this is then we have this. So for any such a weight, we have this inclusion with equality. If and only if either mu is, no, sorry, this is not true. Either we have equality of variety, or this is a bit weaker. We cannot claim that mu is lambda q, but the corresponding ideal in the enveloping algebra is the same. Or G mu is equal to this one. So this is slightly weaker than Barbach-Vokan, but when we will go to now to the setting of BRST reduction, so that is to say the setting of W-algebras, the statement will be slightly nicer. So as Drazen says, sometimes by doing BRST reduction, things are simpler in some sense. All right, so I think it's all what I wanted to say about the results. So now I would like to give some motivations and applications. So as I say, the main application is for W-algebras, so maybe I go directly to that. So rationality. So any questions so far? So I spend the rest of the talk to give application to W-algebras. Okay. All right, so here I keep Drazen's notation. So I pick a nilpotent element F, and then I denote by WKGF the corresponding universal W-algebras, which is obtained by BRST reduction from the universal affine vertex algebra. And so here, by result of Desolé and Katz, we know that the associated variety is wrong, no? Yeah, of course, he is happy. Yeah, it's a nice result. So this is a Slodový slice associated with F. So where here I embed F into an SL2 triple. So here I explain the associated variety. Here is G star with the constant Kirillov-Souriau-Poisson structure. And here the Poisson structure is obtained by Hamiltonian reduction from it. All right? And so now what is nice is the associated variety have a nice behavior with respect to with BRST reduction. So now for any graded quotient V of VKG, so this is a result of Arakawa. The associated variety of the corresponding BRST reduction is the intersection with this one, with this Slodový slice. And so in particular, this one is, yeah, maybe I just mentioned this. This one is just a point, F, if this one is the closure, the nilpotent orbit associated with F. And such a vertex algebra are called, we already encountered this property, but this is a Lie vertex algebra, or C2 cofinite. Okay, so this is what I wanted to mention. And so the Lie's condition is very close to the rational condition. In the definition has nothing to do a priori, but there is a conjecture of Zhu saying that rationality should imply the Lie's condition. So I recall this conjecture that rational Lie's condition. So of course, if you search rational W-algebras, you first concentrate on Lie's W-algebras. And in the setting of W-algebras, we have the following conjecture, which is now a theorem, which was recently proved by Macrae in full generality, and conjecture for a long time by Katz and Kimoto. Okay, and maybe I should mention other people working on this conjecture. So Arakawa, Jethro, and Tomoyuki. there are also particular cases by Justine Fasquelle, and also after that, Kreutzig-Linso, and so on. Okay, and the statement is the following. If K is admissible, and I pick F in the orbit OQ so that the corresponding simple quotient of WK, so this is my notation for the simple quotient of the universal W-algebras, is Lis, because this is a quotient of this one. So the intersection is just a point. This is Lis, and this is the statement, and this is that this is also rational. Okay, so this is a very beautiful result, but what is the connection with our statement? So the connection is that in this setting we can state a minimality property using the weight that appears in our result. Yeah. I should stop now. Okay, I just state this. So connection with link with our result. So maybe I state like this. So assume as before, so K admissible and F, I pick F in the corresponding nilpotent orbit OQ. And then the statement I want to say is that if, so we always, we still have this condition, and then because it's rational, but maybe I don't need to say this. So the statement is that there exists a unique simple WKGF module with minimal conformal dimension. And also this minimal conformal dimension that I write like this is actually Z1. I don't give detail, but Z1 corresponding to the previous one, as you can expect. So in the sense that is Z1 corresponding to the BRST reduction of UG over J lambda Q. Okay, so this conformal weight can be computed thanks to the lambda Q that we obtain. And why this is interesting? Because we have a conjecture which is a bit more general than this, and this statement proves the conjecture in this setting. So I finish with this conjecture to motivate that result. So in fact, we have the more general conjecture that if V is rational, Lis, conformal, and self-dual, so you have a finite set of simple modules, and the conjecture says that there exists a unique simple V module with a minimal conformal dimension. So if I want to be more precise, let's say that this is a set of simple V modules, and so there exists a unique simple V module, let's say I0, with minimal conformal dimension. So this means that this one is strictly bigger than the other one. Okay, so maybe, and so our result proves this statement for W algebras. So. Minimal means the other direction, yes. Yeah. thank you. Yeah. Yeah, what I wanted to say is that this conjecture, okay, for WKGF with K admissible and F in OQ. And this is nice because there is a result of Wang saying that if V is rational and with this condition plus this, then the category of V module is a modular tensor category. So in other words, if this conjecture is true, this means that we can drop that condition. And this is an evidence of this conjecture. Okay, so now I stop here.
Any questions? If you're in Zoom, feel free to unmute yourself and ask. Right, so I can probably ask a quick one. Can you say something about this? The other conjecture you have about like lease being implying irreducibility for the?
Sorry.
Can you say a little bit about the intuition behind the conjecture that lease implies irreducibility? Well, finitely, no, quasi-lease.
Okay.
Finitely many symplectic leaves implies irreducibility of the associated variety.
What do you want I say more about this?
Well, where does it come from? How? Besides having examples, how do you relate these two concepts?
Okay, so the statement is this: this has finitely many symplectic leaves. Then, in fact, it is irreducible, so it is a closure of some symplectic leaves. And evidence is all example, because each time it is in the nilpotent cone, for instance, in the affine setting, this is true. But we don't know, it's probably not true that our list is exhaustive, because from the for D to D duality, we have many other expected examples. We also check that all corresponding K's in W-algebras is also irreducible. And this is more tricky because what you obtain as typical variety is this kind of nilpotent Lodovi slice. And in general, this is not irreducible. Geometrically, it means that this one is unibranch, and there are examples of nilpotent orbit which are not unibranch. But what we hope is that this never happened in the context of vertex algebras.
So you can also explain Ginzburg's result.
Now? No. Yeah. Oh, you mean the one with the filtered associated varieties? And oh, okay. Okay, yeah. Yeah, and maybe this is something I wanted to mention also, is that it's rather about how to prove this, about the new filtration that we have. But okay, what Tomoyuki wants to say is that why we conjecture this, it's because we have, first of all, there is an irreducibility theorem in the setting of primitive ideals, but it's not clear how to see the connection with this condition. So Ginzburg result says the following: if you have a filtered associated algebra, so typically enveloping algebra, because I assume that the corresponding graded A is commutative, and more precisely is a coordinate ring of some reduced scheme. And then for any, the statement is that if you have this, X is naturally a Poisson variety. If X has finitely many symplectic leaves, then for any primitive ideal, then the corresponding variety, so again in Gre A, similarly to before, is irreducible. So again, it is the closure of some symplectic leaf. So this you can recover the irreducibility theorem for primitive ideal. It's not direct because, of course, G does not satisfy this, so you have to quotient. But anyway, so this is why we came to this. And now, what I wanted to mention, but I didn't have time, is that, so probably you know, but RV, I explained the definition. And this actually corresponds to the quotient of the first term of the Lie filtration. Is it okay, sir? Yeah, I guess so. And then recently with Tomoyuki, we find another filtration. So this is another filtration. I don't explain detail, but so that if you consider the first piece, this corresponds to the reduced variety. So this seems to be more appropriate also if we, it's very important. So the motivation is to study this conjecture because if it is a good filtration, we hope to use micro-localization techniques to do that. But the second motivation is that reduced scheme is more appropriate, for instance, if you see this as Higgs branch, because Higgs branch is supposed to be reduced. So this definition is not so well appropriate for this setting. This is what I wanted to mention, but then I didn't mention.
Any more questions? Okay, if not, let's thank the speaker again. And we continue shortly.